Hi-ho, Kermit the Frog here with another fast-breaking news story. There, see, I started it differently. Okay, so here we are again. Is chapter 7, section 4, talking about confidence intervals for variance and standard deviation. And here we're going to example 7-15, page 402. Okay, and they are telling us to find the 95% confidence interval for the variance and standard deviation for the number of named storms per year in the Atlantic basin. A random sample of 10 years has been used. Assume the distribution is approximately normal. Okay, so we have a random sample and the variable is approximately normally distributed. Okay, and so it just gives us the raw data right here, and that's all. that's where we are. So notice what I'm doing here is I'm just I wrote out all the data, and then we don't need to average the data. We're not going to sum these up and divide by the total number. What I'm doing here is I'm taking x, and then next to it I'm creating another column here for x squared. I should know this one. I don't remember. No, this one's 256. Okay, and after we've got all of the x squared values, then what do we do? Let's see, 18 squared. I should know this. It's 324. Then what do we do? Yes, that's right. Then we add them all up, and then we plug them into our fancy formula for sample standard deviation or sample variance, right? That is going to be n times the sigma of x squared, all right? Subtract from that the sigma of x squared, all divided by n times n minus 1. Okay. All right. So I pulled that out of my head, out of my memory banks, and I'm hoping that's right. You can maybe pause and look that up for me. All right. And I'll proceed on to go ahead and sum these up. That's our next step. All right. Mainly just we have to just be careful that we plug everything in and get that part correct. All right. So you can hopefully track me and see if I'm making a mistake here. So where did I leave off? Plus 13 plus. Okay, well, so this is going to be kind of an example of just recalling how to compute standard deviation, things of that sort, variance by hand. Okay, so finally we'll hit enter. That's all of the values. We get 133. Is that what you got? That's what I got. Hopefully we got the same thing. Right, and then the bigger values, but we already worked those out. Okay. You don't want to. Here's the thing: you don't want to have to square each one of these values as you're plugging it into the whole sum. That would be one thing to avoid. Here, these are values that you can safely work out by hand on scratch paper, and then go ahead and plug in. Right. Sorry, like I often tell anyone who will listen. I can't think and talk and type at the same time. It's all too much. All right, so here we have 10 pieces of data, so n is equal to 10. We got out 1,921 for the total of all of the x squared values. So that's that value right there, 1,921. Maybe go ahead and put that in parentheses, right? Just to make sure we don't read that as a decimal value. We've got a total of 133 here, okay? And so then we square that. One common mistake that I see, I don't like to encourage mistakes. I don't think that I'm telling you to do this. Quite the opposite, in fact. Is what? We will have to. Oh, well, I'm sorry. One thing that I see a lot of the time is this. People sum it up and then square it and put that in here. And then they sum it up and they square it and they do it again. So right here, this number is going to be astronomically huge, or for some reason people will get zero a lot of the time. Just make sure that you're not doing that. Okay, so in the denominator here. Okay, and then we're going to go to the calculator, and I probably could have done that part in my head. We're going to go to the calculator and compute all of that and get our sample variance, right? Let me pause here and you can check my work, okay? Okay, so I plugged in everything and I got s squared is equal to 16.9. From there, we can go ahead and take the square root and we'll get s is approximately equal to 4.1. However, this part we don't really need to know, because it's not asking us to find the sample standard deviation. It's not asking us to find the sample variance. It's asking us to form a confidence interval, an estimate for the true population variance and standard deviation. So there we actually only really care about s squared, not because we need the variance, just more to the point, we're going to plug it into the formula. So remember, for this one, we have to get the whole formula all in one shot. So it's going to be our degrees of freedom, n minus 1, times s squared. So notice that's why we can just stop there. We don't care what s is. As long as we have s squared, we're good. And remember that that's what we're going to plug in right there. We're going to just take that directly and plug it in there. Don't square that again. can't tell you that enough. All right, and then chi squared. And so here, this is going to be the valence for sigma squared. And I'm just going to set it up and, kind of like do the repetitive part right here so that I know that I at least get the correct structure for this. And then I can never remember which one's right and which one's left. If you tell me to make a right turn, I literally have to do this, left, right. Okay, that way. Okay. So remember, if you want to remember it that way, that's perfect. Great. You've actually got a sneaky little thing you can do is just remember that you got to switch them up, right? And so this is going to be the right, and this one's going to be the left. Those are, I'm told that that's the opposite way that it is, right? Or if you want to remember it the way that I do, I'm not saying you have to, then it's going to be like this, right? So that just makes sense to me, because here are the chi-squared value. These values, these decimal values, are the ones that we're going to be looking up in the table. And then second of all, the formula is easier to remember then for me, because we have the smaller values appearing on the left and the larger values appearing on the right. And that's what we should ultimately get out of everything. Okay, so we want the 90%, can't say it, 90% confidence interval. We have our n minus 1, our degrees of freedom is equal to 9, right? So df is equal to n minus 1. All right, so the first thing we're going to go ahead and do is look up these chi-squared values. So we'll pause and go ahead and do that. All right, you do it, and you tell me, and then I'll unpause. How's that going to work? Okay. Okay, so here we are again on the next page. Okay, and there's our chi-squared distribution like that. Okay, so the degrees of freedom equals 9, means our chi-squared curve is going to be kind of steeper to begin with and decrease a lot more quickly as well. All right, so we want the 90% confidence interval. That is 1 minus alpha. That means alpha itself is 10%. Alpha divided by 2 is 5%. And then 1 minus alpha divided by 2 is 95%. So on this side, this area on the left is 0.05. This area, well, I don't know, right about there. On the right-hand side, we're going to have be 0.05. So remember the chi-squared is the right side area. So these are going to match up. And then on the other side, this is going to be the chi-squared 1 minus alpha over 2, or in other words, 0.95. That's going to be that area in that direction there. So that means the area on the other side is 5%. Okay, so here we are down at 9 degrees of freedom. We're all the way over here for our 0.95. So this one is 3.325. Okay, and then where'd it go? 9 degrees of freedom, 0.05 column, 16.919. 16.919. Okay. And then we're going to go ahead and plug in those values plus the value that we have for n minus 1 plus the value that we have for s squared into our previous formula for the confidence interval. We already wrote it down on the previous page, so I guess we're allowed to go back and sneak a peek of it. Or you can maybe try to write it down again from memory. Okay, all right, we'll pause. Okay, yeah, so that's what I got to. N minus 1 times s squared in the top in both of these. On this side, we're going to have chi-squared subscript alpha divided by 2. On this side, we're going to have chi-squared subscript 1 minus alpha divided by 2. So for our purposes, I just wrote in 0.05 and 0.95 there and there. Okay. So n minus 1, we can do that in our heads. That's 9. Remember, we already have s squared, so don't do anything else. Right? That one was 3.325. Okay. All right. And then on this side, we have basically the same thing. 9 times 1, 6.9. All divided by 16.919. Okay, that value is going to be somewhat close to 9. All right, so those ones we got to go ahead and plug in. So 9 times 16.9 equals 152.1. All right, divided by, oh, hang on 1 second, 3.325 equals, on this side, 45.7. We'll call it 45.7. That's it. Okay. On the other side, have the same thing. 9 times 16.9 is 152.1, and then divided by 16.919. So that one is 8.9, and oh, actually, we'll round this one up. This goes up to 9.0. Okay. Oh, beautiful. We have a perfect learning opportunity. Okay, look at this. I got these exactly switched up. In the formula, we have chi-squared subscript 0.05. Right here in the formula, I have that. So I have these values mixed up. Right, this one, the red ink should be here. This would be the lower value. So remember, we're taking the same thing. Over here, we're dividing it by a small value. That's going to be the big one. And then on this side, I should have divided by the large value, 16.919. And so that end result is the same thing divided by a larger value. So basically, just switch these up. Okay, so just making sure you all have the